Hello, Mr. Stone here, ready to look at vertical stretching, also known as horizontal compression here, for starters. So I've got the equation, function, f of x equals x squared. We see that on my rather crudely drawn graph here, but hey, it works. What I want to be able to do is to stretch that so that it's a little bit the rate increases faster. What I can do is I can multiply this, in this case, by 2x squared. Um, this is actually going to be my rate of increase by a factor of 2. So if I start plugging this in here, if I do f of 0, I'm still going to get 0, so I get the point 0, 0. That's the same. I can plug in some other points here. If I plug in 1 for x, that gets me, it would normally get me 1 under the original function, but since I'm multiplying by 2, that's going to give me 2. So I get a point right there, and I'm going to get the mirror on the other side of that. And if I do 2, then I get 2 squared is 4 times 2. That's 8. So I'm really going up there. 3, 5, 6, 7, 8. So when I'm over here, I'm actually right there. So we see that this guy starts to climb a lot more rapidly than the original function does. And that's a way we have of stretching. It's kind of like we're pulling it vertically, making it thinner. Similarly, horizontally it's being compressed. So it's like I'm pushing in from the sides. Okay, you can think almost like a thing of Play-Doh. If you've got like a block like that, and you squeeze it, or if you try and pull it, it's going to end up something that's a little bit thinner and also a little bit longer, vertically at least. So that is vertical stretching, and the way to do that again, as far as changing a function, if I've got f of x, and I'm going to have whatever my original function is here, I'm just going to represent that by my block and some squiggles in here. Take whatever that is and then multiply that by a. Here is the secret ingredient for a. The absolute value of a has got to be greater than 1. If it's smaller than 1, it will change differently, as we will see next with vertical compression and horizontal stretching. So again, I've got f of x is my base function here, is equal to x squared. What I want to do now is the opposite of what I just did. I want to compress it, to push it down some, and also to drag it out some along the sides. So I'm going to, in this case, I'm going to multiply by, I'm going to use the reciprocal of 2, which is 1/2. Okay. Again, this is your rate change. So if I plug in f of 0, that would still give me 0. So I'm going to get the coordinate 0, 0. That doesn't change. I'm not shifting this at all. This is not a translation. If I plug in 1, then I still get, of course, 1 is my x. But then I'm going to get 1/2 or 0.5 for my y. So I'm going to be about right there. I'm going to be a little bit shorter on the y-axis than I would be with the original function. If I do 2, I get 2. 2 squared is 4, but half of that gives me 2. So I've got the next coordinate here, 2, 2. And it ends up stretching like so. Pardon my imperfect drawing here, but we do recognize that it's going out a little bit more slowly. It's climbing vertically, but it is going out horizontally at a much greater pace there. Now the secret recipe for this is you take your function f of x equals there's your representative of what your normal function is, times b. And the rule for b is that b has got to be less than 1. It also quite technically must be greater than 0, because if it was 0, then there would be no function anymore. It would all become, it would still be a function, but it would be a function of all values equaling 0, which is not very interesting. Now we're going to look at reflections, and again, similar process. Really, we're multiplying in all of these cases. First thing I want to do is reflect over the x-axis. So I'm going to use the x-axis here as my line of reflection. All I need to do, let me finish my original function there, is take f of x. In this case, I'm going to leave the original function there, multiply it by negative 1. So it becomes a negative. So f of 0 is still 0, so I've got the point 0, 0. That's right there. F of 1 becomes 1. Negative 1 now, because 1 squared is 1, times negative 1 gives me a value right there. And I've got its matching partner on the other side, because this is symmetrical along the y-axis. I plug in 2, I have 2 squared, it would be 4, but then times negative 1, or making that negative, gives me negative 4. So I'm down there. And it will be a perfect mirror image, perfectly symmetrical to what's on top, but it is flipped over. So the rule there is take f of x times really negative whatever your normal function would be there. That's it. You're just making a negative version, applying that at the very tail end. Okay, last one that we are going to look at. We're going to use a little bit different of a function to make this more visible, because x squared, it's not very clear. We're going to use f of x equals x cubed, and here we go. We're reflecting over the y this time, and the y is our vertical line right here. That's what we're reflecting over. And to do this for x cubed, I'm going to take negative x cubed. This is where I put the negative in. I'm putting it in wherever I have x. Simplified out, actually, it does tend to be negative x cubed, but just know when you're reflecting over the y-axis, apply the negative directly to the x input. Wherever you see that, apply the negative. I can do that here. I can do f of 0. That's going to give me 0. Coordinate 0, 0. Okay. Très bien. F of 1 gives me negative 1. So I've got 1, negative 1. So go 1, go down 1. I can also do f of negative 1 cubed. That would give me positive 1. So I have negative 1, 1. We're starting to see this guy shape up here. And if I did f of 2, well, 2 negative 2 cubed, excuse me, because we have to make it negative there, would give me negative 8. So I've got the coordinate 2, negative 8. And similarly for f of negative 2, that would give me positive 8. I'd have the coordinate negative 2, positive 8. That gives me one guy right there, one guy right there. And I can connect these to as best as I can to make a perfectly symmetrical function here that is symmetrical over the y-axis. It's strangely enough, it's a little bit of a weird case, and that's because of this. It's also symmetrical over the x-axis as well. But I did want to show something that was very clearly reflecting over the y-axis that wasn't too like crazy complex. All right, so please review that, think about that, and I'd like you to see what you can do to transform this function if f of x is equal to x squared plus 4. Try and vertically stretch that by a factor of 3. Horizontally stretch that. How would the function change? By a factor of 6. And lastly, reflect this over the x-axis. All right, have fun with that. Bring your questions. Have a fantastic day.